Thank you very much for the introduction. And also, I would like to thank Stefan and the organizers to invite me to give this talk. And today, I'm going to show you how electron diffraction can impact the studies of MOF and COFs. And you know that everybody is using X-ray diffraction. And X-ray diffraction was discovered 1912, and already the same year, and the structured analysis using X-ray diffraction has been developed, and both of them were awarded Nobel Prizes. But electron diffraction only discovered 15 years after X-ray diffraction. And however, today it is not very much used, I think, for most of us. What is the reason? Actually, even today, the textbook, for example, in physical chemistry, and you see that when we discuss about the crystallography diffraction technique, and the neutron and electrons has only 1 page, and the X-rays has 12 pages. And if you go to the classical solid state chemistry book, and you see that X-rays has 33 pages, electrons only 1 page, electron diffraction, neutron 5 pages, and the electron microscopy 15 pages. I think most of you are familiar with electron microscopy. You're using it for images, but for diffraction, it's not very straightforward. And if you look at this 1 page, actually less than one page description of this book, solid state chemistry, you will see that actually most of the things are very negative on electron diffraction, even the text. So first, it starts with the disadvantage of the electron diffraction is the secondary diffraction commonly occurs. So this we call also multiple scattering, because electrons interact very strongly with matter. And so the intensities, the intensities of diffracted beams are unreliable. It cannot be used quantitatively for structure determination. So it's very strong statement. And the technique is used for determining unit cell space groups. In spite of that, diffraction is underused, and because it is time-consuming and requires high level of expertise for data interpretation. So, however, of limited use of the structure for full structure determination because of the unreliability of diffraction intensity. So 2 times in this less than 1 page text talking about bad diffraction data. And it's also right, electrons is unsuitable as a routine method for phase identification in relatively large samples, and because of the sampling issues. So this 1 page description and quite a lot of negative things, and which is really true. And when why electron diffraction was not really very much used. So the general is electron diffraction intensity is unreliable and cannot be used for structure determination. And electron diffraction unsuitable as a routine method for sample phase identification. And so that's why, so today, over 1.2 million crystal structures solved, deposited in the CSD database, and most of them were solved by X-ray diffraction. And however, there is a problem with X-ray diffraction. We need large crystals. It's not always easy to get large crystals. So why not electron diffraction? Actually, if you have powders, if you use powder diffraction, you get a powder X-ray pattern, and it's 1D. But if you use the same powder and look at it in the microscopes by diffraction, you will get a lot of data and completely 3D data. So actually, electron diffraction should have been a very important technique for most of you. The early days, so there are some studies using electron diffraction specifically for organic compounds. And for inorganic compounds, it's more skeptical because of the dynamical effects. And so very often we are using zonal-axis patterns because the intensities people think very not very reliable. And so many people, we started to our group use images. So you can obtain crystallographic phase information directly from images, and you can combine it with electron diffraction data. So this is the example. So we can obtain the phases from images and using the amplitude obtained from electron diffraction. And so this is the map you obtained directly from this image. So very high atomic resolution, as you see here. And we also showed later when you can observe the structure from images and then refine the structure using electron diffraction data. And so because electron diffraction data extend to much higher resolution compared with images and easily to obtain. And later, we also showed that it is possible to directly solve the structure using electron diffraction. So this is directly using direct method and obtain this structure. And it really works with zonal-axis pattern, but those examples are mainly for 2D, and you have a very short zonal-axis axis, so that the atoms do not really overlap. And for 3D structures, it will be more difficult. And so you need to collect the data from different orientations and combine those data together. And we showed with an example, combining high resolution images where you can obtain phase information. These are a few examples, images obtained from different orientations. And this was done already after crystallographic image processing, so that where you can get the phase information directly. And so we combined amplitudes from the electron diffraction data. We used 13 different projections, combined them together. Finally, we could get such a very nice structure model, so where you can locate all atoms almost. And so basically, you can solve the structure using electron diffraction in combination with images for very large structures. And the problem is that this is very demanding. And so this took us 7 years to solve this structure. And it's very high expertise to do what to do. And how to have the technique that could be used by most of the people, like chemists who make synthesis, and you need a very fast, easy technique. And so diffraction is a good technique because it's easy to obtain. The problem is it's really hard, has dynamical effects, as you see here. So these 3 diffraction patterns obtained from exactly the same crystal, but just from different thicknesses. So this is from the thinner part, and you move the aperture, you select the thicker one, you can see the diffraction intensities change dramatically. And of course, nobody will believe that this data would be possible to get the structure, because based on the structure determination is based on the intensity. So what we do? And the 1994, it's a good news because there is a new technique called the precession electron diffraction. And what you do is that you tilt your beam, and from the zone axis, you precess it like around. And so these are the diffraction pattern you obtained at each moment during this precession. And if you use this, combine this diffraction pattern together, you get such a diffraction. So look, the diffraction looks like 2D zonal patterns. Actually, it is obtained from many diffraction patterns together. And this one is comparing with without precession. You see that the intensity is changed a lot, and you get also much higher resolution. So this actually shows that dynamical effects were reduced if you take diffraction patterns from off-zone axis. And nobody thought about it before. And so this was kicked several development of what's called now 3D electron diffraction. And in life sciences, they call it micro-ED. And so there are several groups who developed this different protocols for 3D ED. With the Korps group in Germany, in Mainz. So her group developed it's called automated diffraction tomography. And our group developed it's called the rotation electron diffraction. And later Termigona's group developed the microcrystal electron diffraction they called the micro-ED. So principle is the same. And so you tilt the crystal from arbitrary orientation, tilt it continuously, and then you collect the 3D data. And most of the data will be off-zone axis data. And at the beginning, and we use stepwise data collection. You tilt the crystal and collect small steps to collect the data, small steps to collect the data. And in the Korps group, she combines precession with rotation. And in our case, we combine electron beam tilt with rotation. So that's a different geometry. So this is how the data could be collected. And when we combine the beam tilt, so we could collect like 1,400 diffraction patterns in an hour, and with small steps. And later we can combine these ones in the software and determine the unit cell space group and extract the intensities. And afterward, you can use this information for either face identification or structure determination if you don't know the structure. Face identification is done by combining the unit cell parameters and the space group. The first MOF structure determined by 3D ED was done by the Korps group. So this was the structure. It's called the MFU4L, and so this is the structure. And by that time, and you are able to get 1.3 angstrom resolution with the stepwise technique. And the first Korps structure determined was from my group in collaboration with from Yagi, and this is the Co-CAU-36 MOF. You can see that you can obtain very nice single crystal data directly from this MOFs. The resolution was not very high, 1.5 angstrom. Still, we were able to locate all the atoms in the structure. And we found out actually with temperature and the structure changes. As you see here, at the low temperature, the structure was more contract. At room temperature, it's expanded. So it's 9-fold symmetry, interpenetration. And so electron diffraction could be used, but basically for MOFs and the COFs, usually you get relatively low resolution, and you would like to have higher resolution because they are not very stable in the beam. So, and that is why a lot of technique has been developed. So this is called fast electron diffraction by continuous rotation instead of stepwise rotation where you collect the data. And so you continuously rotate the crystal in the microscope, and then you take diffraction as a movie. And so this is how it looks like. So you tilt the crystal and you get a lot of diffraction patterns. And if you have a very fast detector, and then you can take the data very, very fast. And so how fast can we collect the data? Still, the data is good enough for structure determination. So this is an example. As you see, the data was collected only 70 seconds, and it's extended. It's a MOF extended to 0.82 ounce resolution. So with this data, it's very straightforward to obtain the structure. And what we actually use with the continuous rotation data is all the existing software developed by X-ray diffraction. And you just collect the data, and then you use scattering factors for electrons and the wavelengths for electrons, and the rest of the things is like as if there were X-ray diffraction data. So you can use exactly the same thing. So this makes it much faster, easy to process the data now. This is processed with the software XDS, or X-ray software are free. So everybody can use. You can refine the structure now, not only solve the structure and get a very high precision of electron diffraction model. And so this is the model you obtained. So we are able to get atomic precisions for all atoms directly from the structure solution. And we apply kinematical approximation. So because X-ray software, they assume everything's kinematical, and we use them. So it's kinematical approximation and kinematical refinement. And as you said, they are dynamic effects. Yes. So how it will be reflected? So we generally have a higher R value than what you see for X-ray diffraction. And this high R value doesn't necessarily mean that your model is wrong. It's more related to how much dynamic effect you have in your sample. But still, the model is still correct. And just one example, so when you have very beam-sensitive material, so it's generally a large pore, MOFs usually is less stable. As you see here, this one, and this CAU-45, it's from Nobel Stokes group in Kiel. And you see here that we were able to determine the structure, very good electron diffraction data, very, very small particles here. And the pore size is very large. And also we can find out actually how these linkers are connected, and also there are disorders in this linker, and it can be directly identified. And so it's now very straightforward to obtain structure model. So this is the technique has been really used in our lab routinely, and this is the work by Eric Grab and Ken Ing, and they make MOFs, and now today they very seldomly use single crystal X-ray diffraction, mostly electron diffraction, solve their structures, and it's much straightforward. So this is one of the structure they were solved, and you see that it's Eric will give a talk tomorrow, so I hope you can join. And this, we can also do images. So as you see here, you can get a very nice image also from this nice MOF. And this was done by Tom Viharma in our lab. When you make synthesis, you very often get multiple phases. So it's actually possible to study using electron diffraction, multiple phases samples. You don't have to purify them. So this was an example, a sample obtained from Carpenter-Lee's group. And you can see already from SEM images that there are two different morphologies of the sample. And my student, Laura, collected data, and from this octahedral shaped sample, and she collected data. It turns out it's the UIO 67. And the resolution was quite high, and it could directly solve the structure. And for the plate-like samples, and it turned out to be MOF2022, and the resolution is even higher, 0.8 angstrom, and you can also solve the structure. So from one mixture of everything, and you can pick up individual crystals to get very high quality structures. Not only in the structure is good, and actually you can look at more details, structure details, for example, disorder, and maybe even the molecular motions. When we look at the data of refined by of the UL67, as you see here, you can find that the atomic displacement parameters, we refine it anisotropically. You see they're elongated, and it turns out actually these are actually thermal motions, so it's the same as what you can find in X-ray diffraction. So the model is already dissolved, and this agrees very well with X-ray diffraction. Also, our resolution is slightly lower than their X-ray diffraction. And we can also see some disorder of oxygen, and it is found out also in the model. More importantly, so we can really see the motion of different linkers in the pores. As you see here, in this MOF140C, there are two different linkers, symmetry independent, and one of the linker looks has a very normal ADP, or the atomic displacement parameters, and the other linker has much larger ones. We find out actually this linker has more flexible than the linker 1, than linker 2, because this linker is isolated, and this linker has a pi-pi stacking with the next one, so they are more stable. So, all like here. So the details can be easily obtained using electron diffraction today. And so we can probe. So this is how the movement of the linker obtained. So how accurate can we obtain structures? Actually, we compared our data with single crystal X-ray diffraction data. This is the JFC Paula mentioned yesterday, and you can see that by combining the diffraction and the diffraction and the X-ray data, and the deviation is on the second decimal. So this is the accuracy we can currently obtain by electron diffraction. And comparing X-ray diffraction with powder X-ray diffraction with electron diffraction, you can see also that we're also in the same range. So currently, electron diffraction can give you very high accurate structure. And we can also see hydrogens. And this is the example. You see, we refined the structure. This is a hybrid structure. And so you can see all the hydrogen positions could be located. And using these hydrogen positions, we are able to study all different no-covalent interactions in the structure, which is quite important if you want to know. And most of the time, if you have poor data, and it's possible to use dynamical refinement to obtain hydrogen positions. And depends on your data, so you can get the good results. And for MOF community, for zeolite community, we were asked, can we really locate gas molecules in the pores? Because this is the important property for the porous materials. And we studied some examples. We want to know really when and how we can obtain the gas molecules. So this is a structure we synthesized a long time ago solved by single crystal X-ray diffraction, a germanate. And we can really see that you can get atomic positions. With electron diffraction data, we can see in the pores, as you see here, these are the models. And so these are the peaks we obtained in the pores. And they are very isolated. And you can just connect the peaks, directly obtain the gas molecules. And in this case, there are two different configurations of the same molecule, and it can be directly obtained. By comparing the X-ray model, this is the X-ray model, this is the electron diffraction model, superimposed the X-ray model. So you see that all the organic molecules can be directly obtained. If you have more stable, unstable samples, so you can cool the sample. So this is the data collected at 100K, 96K. So you can find that with water molecules that form a hydrogen bound network that can be directly located, and also the solvent molecule can be directly located. And with this, currently the 3D data in our lab, and the data collection is quite routine. And so a lot of structures could be solved. So we have solved more than 250 structures during the last few years. And it includes MOFs, many MOFs, and also COFs, and even HOFs. How to, because the data collection is so easy, and how to make it more automatic. You would like probably to get the structure while you are collecting data. So we developed this online structure solution so you can collect the data when the data is collected, and the structure could be, the data processing is directly carried on during the data collection. And so that the structure solution can be obtained within 3 minutes. So this is, you see that this is the automated data processing. And for data collection, we're trying to also make it more automatic. So we developed this platform, it's called Instamatic. And so it's for data collection and data processing, and also with this structure solution pipeline. And that includes like crystal screening. So you want the computer to tell you which crystal to collect the data from, and you want to find the suitable crystals and to collect the 3D data. And so the data collection will be also needs the crystal tracking, because when you tilt the crystal may move, and you don't want to lose the crystal. And for data processing, and we integrate the existing X-ray diffraction software, and access an online solution. So two methods we developed is called cRED and cRED. So these two are for high-throughput data collection and the structure determination. And so this is how we do the cRED. The concept is that you collect one diffraction per crystal. So you scan through the grids. So this is the grids, and so you see here, each grid you have an image, and from the image you pick up where you want to collect the data. You go there to collect the data, and you move to the next one. So this data collection is fast. Currently in our you could collect more than 3,000 diffraction patterns per hour. And in the new microscope, we can collect even much faster. So with this, and now the sampling problem obtained by electron diffraction may be solved if you collect enough data and you have large sampling. And however, when you have so much data, you cannot do the analysis by yourself anymore. And why we should just collect one diffraction pattern? And that is because for very beam-sensitive materials, you really can get much higher resolution because you put all those in one diffraction pattern instead of a 3D diffraction pattern. So as you see here, it's an example. It is a zeolite. When we had the rotation electron diffraction stepwise method, the crystal, we could get only 2.5 angstrom resolution. When we use the zero electron diffraction, which means you collect data continuously, and we could get 1.5 angstrom. By zero ED, this is one diffraction pattern, and we could now get to 0.8 angstrom resolution. And so when you have such a high resolution, of course, the structure determination will be much easier. How do we do that? Because we have so many crystals, we can scan all the crystals that you see here. This model was obtained by combining almost 400 crystals, and each crystal have one orientation, and you combine them together. And so you can determine the structure not only, and also you can find all the gas species in the pores. So this is the way if you have two beam-sensitive materials. And when you have such a data, of course, you cannot really do it by hand. And so my postdoc developed it's a neural network method for learning what is the good diffraction pattern, what is the better diffraction pattern, and you give the scores to all of them. And in this way, it is possible to identify, to just look at the good diffraction patterns. And using this one, and you can see that we applied it in the MOF CAU-36, and this is a data you collected. You can you see that more than 1,200 diffraction patterns could be collected within half an hour. And when you have so many diffraction patterns, and you can do the analysis, and we find out about 500 diffraction patterns comes from the CAU-36, and some of them, and very differently, and they are from impurities. So it's very good method to detect impurities also. And if you find the impurities or new phases, and you can go there because we know where the crystal is, and recollect the series data and solve the structure directly. And I would like to also mention that with electron microscopy, you can also study the chemical compositions on the same crystal. And so it turns out this is just a precursor of the sample. When you have such a short data collection, so you would like to have the data collected automatically on the 3D data. So this is, we call it the serial ED. So it's ultimately the data collection of the serial data. And this, as you see here, and we tilt the crystal, we collect the data, and we do the automated data crystal tracking. When the data is collected, and we move to another crystal and continue to collect the data, 3D data. In this way, when the data is collected, we can do the data conversion, also data processing online. When you have, again, so much data, you cannot really analyze it by hand. And so my postdoc staff developed this called Edtools to how to analyze all the data, processed, and merge them together. And so you can see that when you have, it's called hierarchical clustering. First, it's based on the unit cells. For example, when you, this is the example, the data collected, we find out that there are two different phases. One is two different zeolites. And then you can look at this group and to see how the intensities agree with each other. Sometimes you have samples, structures have similar unit cells, but different structures. Then it's important to compare the intensities. So you can do the clustering based on the unit cell parameters and also based on intensities. In this case, we were able to select the intensities that agree with each other and to merge them to get more complete data. And specifically for beam-sensitive materials, you can use short, small wedges and collect more data from different crystals. And so in this case, you can solve the structure by combining this data by selecting using this hierarchical clustering. And I give you one example, and this is combined with the high throughput synthesis. I think many of you are using. When you make the synthesis, you will do a lot of experiments, and sometimes you get some very complicated powder patterns cannot be indexed in single phases. And so one example is this one. So this is the sample we have. It looks like this, and the powder pattern is very complicated. We applied serial electron diffraction data. So this 3D data collected. This collection is done automatically. So it's like you can obtain 340 crystals within 6 hours. You can do it in the night. And when you have this data, and we did the clustering to process the data, and we find out actually there are plenty of phases in this sample. They are starting phases like germanium oxide, and there are 5 different zeolites in the same batch, and there are 3 major phases, and there are 2 minor phases. So this one was founded twice, as you see here, and this one was founded once. And you could identify the phases, and you have 3D data. You could also solve the structure if you don't know the structure. And so actually, if you look at the powders, you found out, yes. So if you just index the powder with this zeolite, and you see extra peaks in the powder, and you add another phase, and most of the peaks are already indexed. There are a few more, and when you add 3 phases, almost all the peaks are indexed. So the fit was quite well, and all these 2 phases are almost invisible by powder XRD. You will not find it, and it's possible to get it directly from electron diffraction. And many people said, how difficult it is to make the sample. It's much easier in a single crystal X-ray diffraction. And because you just have a powder, and if it is large, you probably crush it to make it smaller, and you spray it into the carbon, the grade. And if it is, you can do it in dry powder if your sample is sensitive to solvent, just like this, pick the crystal, and you charge a little bit of your some grade so that it's a little bit charged, you can get some crystal zone. Or if you disperse in the solvent, if your sample is stable, and to put a drop or 2 in a filter paper on the grade. And and if your sample is very beam sensitive and not stable, if you want to study the gas molecules, you can use plant phase to study it in liquid phase. And so use these ones, so it's possible to study now the COF structures, and COF structure can get a very high resolution, like 1 angstrom, and you can see the different phases, the expanded version and the contracted version depends on if you cool the sample before you put it in the microscope or after. And we wanted to see that if you are able to do some in situ studies, and you can use the in situ holders, and you have gas holders, liquid holders, and this is the one we were collaborating with Christian Moelcules in the Denmark, and this is a nano channel, as you see here. So you can have gas of liquid inlet and outlet, and you have the window where you can observe your crystals. This is what you see here, and with this, we were able to solve see that you can see the crystal here, and collect the data. This is nano channel, and then you can obtain the structure. So you can obtain the structure in liquid, and this is grow inside the channel, the crystals. And we have, if you want to know more, so we have written a protocol exactly how, step by step, how we obtain, we make the sample and obtain the data and solve the structure. So you're very welcome to see, and even with the troubleshooting here. Now, there are many different versions of possibilities if you want to use the technique, and they are homemade ones that we have here, and there are also commercial software like commercial electron microscopy facility, and also specialized diffractometer. So I think now it is, you can have all possibility to have the access to the technique and to use it for your data. This is finally my conclusion. So actually, electron diffraction has been now come to the revolution, and so you can really study the accurate structures of unknown samples. You can do phase analysis. You can also study a wide range of samples, and so this was already appointed as the one of the 10 breakthroughs 2018. And now it is the opportunity for you to use the technique and to study your materials. I hope that in the future that this technique will be in every people's lab. And with this, so of course, because of the technique now today, so even the IUCRJ has a new session for electron crystallography. Now I think it's no longer skeptical, and everybody will be able to use the technique. And finally, so I want to acknowledge my collaborators and my group members who did the work, and the funding agencies. Thank you for your attention.
Thank you very much, Professor Zou, for this very, very nice overview of the powerful techniques you've developed. There are questions in the audience, I'm sure. Yes.
Thanks for the opportunity.
Thanks, XiaodongZou, very high technology. I have a question, very general. Can you image materials like amorphous materials and semi-crystalline materials? Thank you.
Yes, you can do diffraction with amorphous materials. Then it's a different technique. It's called powder, the PDP, pad distribution function. And also you can use 3D delta PDF. So there are, I don't have time to talk about it.
Thank you. Second question.
Thanks again. Dear Professor Zhou, thanks for your lectures. I'm Jianbo Song from Hankel Group, a PhD student from Hankel Group in Dortmund, and at my last phase of my study. And I have listened to your lectures for many times, and the technique is now get more advanced and more precise and even faster. I wonder two questions. So first one is like, have you ever measured a sample under cryogenetic atmosphere to prevent the sample from beam damaging?
Yes, and we have done a lot.
Okay, cool. If so, I wonder, like, if one day there is a possibility that we can measure some, determine the structure of some organic complex, like a protein, molecular, or some virus, to just determine the structure, or even maybe with combining with cryo-electron microscopy. I think that will be.
Yeah, we have done that. I haven't shown that. We have studied a lot of pharmaceuticals and also proteins, crystals.
Then that's really advanced. Thanks.
Thank you. We'll take one final question.
Also, many thanks from my side for this brilliant presentation and all the opportunities you're offering to our community, you have omitted one special topic, namely absolute structural determination. Is it possible also to distinguish enantiomorphic forms of crystals?
Yes, so I haven't had time to talk about it. And if you can determine the absolute structure, then you need to apply dynamical refinement. And so it's possible. We have done in collaboration with Lucas Palatinos many different types of structures.
Thanks a lot. I encourage you to applaud once again Professor Zhu.